Good morning, good afternoon, good evening, wherever you are in the world. Welcome to our first of many events called Code Unboxed with TrustInSoft. Today, we're going to be running through analysis of TinyCrypt. Before we get started and I introduce you to one of our senior analysts, I'd like just to talk through a couple of housekeeping rules. This event or this webinar will be recorded for on-demand viewing at a later stage, and we'll provide the recording link to everybody who's registered so that you can view it at your leisure. We will open it up for questions at the end, so please have those questions prepared, and you can just put them in the Q&A area or the chat area as well. As I mentioned, this is the first of many events for the Code Unboxed series that TrustInSoft is going to be doing. One thing I'd just like to point out as well is even though today, as I mentioned, we're doing TinyCrypt analysis, we do follow a disclosure process for any of the open source code that we are showing analysis of. Where we stick to a 90-day notice. So obviously we've done the analysis already on the code, so we know what we're expecting. We're just sharing the analysis here on this call. We do disclose any of the bugs or vulnerabilities that we found during our analysis 90 days prior to the event. And we do also have a 30-day notice period with the owner or with the publisher of the respective source code about the respective event. In fact, today's event, the owners, Intel specifically, were notified about the event, and from a disclosure perspective, the UBs that we'll be running through were disclosed a number of years ago, in fact, about TinyCrypt. We definitely want to remain good citizens in the cyber world, and we're not going to show any vulnerabilities that have not been notified to the respective owner, as well as have not necessarily been fixed. Some of the vulnerabilities are still available and have not been addressed, but we want to do our part as part of the greater community. So on that note, I'd like just to introduce one of our senior analysts and trainers, Clément Gillard. Clément.
Thank you for having me. I'm glad to be here and finally be able to share the work that me and my colleagues did on TinyCrypt.
Awesome. So before we get started, if you're not familiar with TinyCrypt, TinyCrypt is an open source cryptographic library. I'm not going to go through all the details, what it does and everything. Some of the use cases, it helps with securing communication, data integrity, and secure storage. It has been used quite a lot in the past. I don't know how much it is used today. It is still available as an open source solution, so you can go and check out the respective code. A little bit about TrustInSoft and what we do. Very high level, we empower developers to deliver mathematically proven zero defect products. What does that mean? Well, from a TrustInSoft Analyzer perspective, we use abstract interpretation and formal methods where we help provide to developers testing tools to exhaustively test their respective code through billions of tests with generalization inputs, as well as providing mathematical proof that there is no UBs or undefined behaviors within the respective code. So what do I mean by undefined behaviors if you're not familiar with it, and specifically formal methods? When one is performing static analysis, what generally happens with many static analysis tools today is some of the respective code paths in code is missed. And when you miss some of those code paths, there are some real-world impacts that can result. Most people have heard about Heartbleed. Heartbleed was an OpenSSL issue, which was a result of improper input validation, and it impacted hundreds of thousands of web servers around the world. So it's a little bit old, but if you've been around for a while, you'll be very familiar with Heartbleed as well. This year, in fact, VMware published, and I suppose a CWE and CVE talking about the fact that someone could do a VM escape, and the result of that, the root cause of that was an out-of-bounds write. And then probably one of the most expensive bugs known is the Ariane flight V88 failure, which resulted in a rocket exploding and cost in excess of $370 million. So I think it's up there with one of the most expensive bugs in history. With exhaustive static analysis and utilizing formal methods, you are able to test all of those respective code paths and ensure that mathematically you can guarantee that there are no existence of undefined behaviors, which result in some of those real-world issues that I pointed out there. So on that note, I'm going to hand over to Clement just to talk about some of the analysis that he's done and talk a little bit more about TinyCrypt.
So as Gavin just introduced, TinyCrypt is an open source library. It's developed by Intel. The goal of TinyCrypt is to be a small cryptographic library with some basic modules that you can reuse in your projects. Let's look at the architecture of this library. In the lib directory, under source, we find implementations for various cryptographic algorithms separated in modules. Like in lib, under include TinyCrypt, we find headers for those modules. Finally, back from the root, under tests, we have test programs that instrument each of those modules. I have here a fresh clone of TinyCrypt. We create a TrustInSoft project with the command tis init. It will create a directory TrustInSoft with some skeleton files that we'll have to fill in to build my analysis. I will first edit the prepare script. This script contains all of the actions that must be performed before we start doing analysis. For TinyCrypt, this will be making the tests. I also want to be running that with bear so that I have a compilation database. And I will also run make clean to remove all of the unwanted build artifacts. I can now run that script with the command tisprepare. We'll build, then clean, but in the end, I have my compilation database that I will be able to reuse with TrustInSoft Analyzer. The next step is to start writing a configuration for the analyzer. We do not need all of those comments. Let's clean this up. This is the configuration I'm going to use to analyze the AES module. I simply give it a name, then the list of files. And for this analysis, I will use TrustInSoft Analyzer in level 1 interpreter mode. To run this analysis, we can use tisinspect with the name of the analysis. This will perform the analysis and then start the inspector so that we can look inside. The analyzer is giving me an alarm signed overflow in function tcaes set encrypt key. Looking at the source code, we are reading values from an array k, then shifting them, then ORing them, and then storing the result into an array words. Here, k is an array of 8-bit unsigned integers, while words is an array of 32-bit unsigned integers. Looking at the alarm, you can see that the operation that the analyzer is complaining about is the shift by 24. This should be correct, right? 8 plus 24 fits into 32. Well, the analyzer is complaining about signed overflow. Indeed, if the operation was done as signed, by taking an 8-bit positive integer and shifting it by 24, I could end up with a 32-bit positive integer when the largest positive signed integer, int max, fits in only 31 bits. So why is this operation done as signed in the first place? Is the analyzer wrong here? Well, in interpreter mode, TrustInSoft Analyzer does no approximations, so something definitely is wrong with this code. I have here a copy of the C17 standard. At section 657, bitwise shift operators, it states the integer promotions are performed on each of the operands. Integer promotions are defined a little bit earlier in the standard, and in our case, it indeed calls for a conversion to signed int. Back to the definition of the shift operators, it does state that for signed types, if the result is not representable, the behavior is undefined. So here, we indeed have a bug. There is an implicit cast to signed int, which makes the shift by 24 invalid for some 8-bit values. The analyzer has made this cast explicit during its parsing, and that's why it's shown here in the normalized code. Undefined behavior means the compiler could do anything, and here the most likely outcome is that the compiler will output instructions that could mishandle the 32nd bit, which could lead to a loss or corruption of data. The proposed fix would be to add an explicit cast to unsigned 32-bit here, so that when the operation happens, it still is unsigned after integer promotion. Now that we have edited the code, we need to save and then run the parsing again, and then run the value analysis again. We find a similar bug later in the same function. When using macro subword, it also expenses the shift by 24, which also happens as signed because of integer promotion. We fix by making an explicit cast to unsigned before the shift in the macro subbyte. And after running the analysis for a third time, we now have there is no undefined behavior on this tested part. Looking into main, you can see that we have gone through test 1, test 2, test 3, and test 4, all successfully. This level 1 analysis is now complete. Since we found bugs in the AES module of TinyCrypt by passing the existing tests in TrustInSoft Analyzer interpreter mode, let's reproduce that on all modules. Now that I have written all of those analysis configurations, I'm going to run them all with the command tis run all and doing up to 10 analyses in parallel. To be able to see all of the results at once, I will generate a HTML report with the command tis report. In the report, I can see that over my analysis campaign, I have 4 analyses that exhibit undefined behavior. Let's start by looking into CBC mode. We open the inspector with TinyInspect and then the name of the analysis. Level 1. We have a call to memcopy, and the analyzer is telling us that the from buffer may not be valid for the provided length. Looking at the values, from len is always 16, and from is always pointing inside of a buffer called encrypted with an offset that goes up by 16 every time we call the function copy. Using the inspector, I can see where from and from len have been set. Here, from len comes from this size of state, always 16, and from comes from this variable in, which also points inside of encrypted with the initial offsets. In is a parameter of the function, so we need to go up. Here I have reached a loop. In gets increased by 16 at certain turns of the loop, and it looks like the loop will do so until it has copied outlen bytes. Outlen is set to 80. Both in and out len are parameters of this function, so we still need to go up. Out len comes from this integer length, which is set just above to be the size of encrypted, or 80. In comes from this pointer p, which is set just earlier to be pointing at encrypted with an initial offset of 16. This is our bug. We cannot read the whole length of the buffer encrypted and still start with an initial offset of 16. We're going to have a buffer overflow. The proposed fix would be to decrease length by TCAS block size. That way, it will counteract the offset that was given to P. And after saving the modification and running the analysis again, we no longer have alarms in this analysis. Let's switch to the next analysis that had alarms, CMAC mode. Let's first focus on the source code. Looking at this statement, we are reading a value from X, then we do some arithmetic on it, then we store the result in out, then we decrement out, and then we check for the exit condition. What that means is that depending on how out is set up, it's possible that once we reach the exit condition, we have already computed a pointer that points before the start of a buffer. That's invalid, even if we do not use that pointer. The suggested fix is to move the decrement until after the check for the exit condition. That way, there is no risk that at the last loop turn, we go before the start of a buffer. I save, run the parsing, and then run the value analysis again. And there are no more alarms. Next up, CTR mode. Signed overflow in function tc CTR mode. Oh, immediately we see we are reading a value from an array, maybe an array of bytes. Yes, it is. Nonce is an array of bytes. So read a value from an array of bytes, shifted by 24. The rules of C state that there must be an implicit cast to int before we do this operation. But since now this operation is happening as signed, it's not valid for all 8-bit values, and we get to this signed overflow. We already know what this is. We already saw that with the AES module, and we know the fix, which is to put an explicit cast to unsigned before the shift. Let's save, parse, and run the analysis again. And it's fixed. Last stop, HMAC. We are again at a shift by 24, but this time the alarm is not about signed overflow, but about uninitialized memory. If we look at this temporary variable in the normalized code, we see that it is pointing inside this variable dummy state, and when we dereference it, we see the value uninitialized. This is another feature of TrustInSoft Analyzer. Thanks to abstract interpretation, the analyzer can not only propagate concrete values, like integers and pointers, as you would see during a real execution, but also abstract values, like this uninitialized, which signals to me that the program is relying on uninitialized data. We would like to know where an initialization step was missed. For this, I'm going to copy this expression and then I'm going to look into this variable dummy state. It's a local variable, so let's jump to its declaration. We are now in tc hmax set key. Dummy state is a local variable to this function. In C, local variables are uninitialized by default. So when I track what I just copied, we should see just uninitialized values. From here, we can also see the flow of the code. After the declarations, there's some conditions, and then these three calls to tc SHA-256 init, update, and final. The call to final is highlighted in yellow because it's the start of the call stack that leads to the alarm. So our initialization issue must be somewhere in those three calls. Now that I have tracked the part of dummy state I'm interested in, I can look at how it changes at various points in the program. For example, at the call to tc SHA-256 init, I can see that the leftovers go from being completely uninitialized to completely set to 0. So they are initialized after all? Let's continue the investigation. At the call to update, I can see that they go from being completely set to 0 to being partially set to 0 and partially uninitialized. So something must have happened in update. Now, update is a little bit complex, but what we can focus on is this line 76, which jumps to me because we are reading from some buffer data, and then we are writing into our leftovers. So this looks like a good candidate as to what could be uninitializing our leftovers. Let's look at where data comes from. It looks like it's a parameter to SHA-256 update. And it comes from this dummy key. And dummy key is also a local variable to tc hmax set key. In fact, it's defined just above our dummy state. It's a local variable, so it's uninitialized by default. There is no initializer on it. In fact, it's even const, so it has uninitialized values, and those values are never changed. And then they are copied into the dummy state, and then they are propagated up to a computation, and that's why we have our alarm. The suggested fix is to put an explicit initialization to 0. That way, there won't be any uninitialized values. And with that, HMAC no longer has any alarms. I think this was the last of them, so let's run all of the analyses again and generate a new report. And ta-da! Now, all of our analyses show no UB, meaning that we have successfully identified and worked around each alarm in our campaign. Okay, so to conclude, here's a recap of all of the issues that we identified. We found 3 instances of integer overflow. 2 were found in the AES module, 1 in the CTR mode module. So we were looking for the vulnerability, the weaknesses associated with it. And at first glance, because it involves a bitwise shift, it might look like CWE 1335 about incorrect bitwise shift of integer. But actually, this specific CWE does not mention the actual problem of the integer overflow, where the value goes over the correct type. This actually falls under the much wider umbrella of CWE 190 about integer overflow or wraparound. So as I said here, the consequence would be that the compiler issues the wrong operation for the type that is specified, and that might lead to the loss of 1 bit during the computation, which when you think about all of the cryptographic algorithms, that would just mean an incorrect result. You just lost the data and it's not recoverable. Then we found an invalid pointer arithmetic in CMAC mode. Remember the pointer that went before the start during a loop. So this is an instance of CWE 823, use of out of range pointer offset. We got a pointer that was out of the range of the allowed values. Here the consequence would be, again, that the compiler would assume that the computation cannot go before the start of the buffer, and so issue the wrong assembly or do a wrong optimization or an unexpected optimization around the computation. Then we had some uninitialized data in hmac.c. This is an instance of CWE 456, missing initialization of a variable. The consequence, as always with initialized data, is that you are going to leak some data, and that opens the case for maybe some timing attack. This is especially ironic since this specific dummy variable was there to also prevent another timing attack. And then finally, we also had the wrong buffer length computation in the test for the CBC mode module. This is an instance of CWE 119, improper restriction of operations within the bounds of a memory buffer. We compute a length that is too large compared to the pointer that we give. So here the consequences are kind of restricted. We have all of the before, the compiler could issue the wrong operations. Thankfully, this is limited to the test. The library is fine, but that does mean that the test is invalid. So if you look at how the test is organized, you have, I think, 4 or 5 tests of CBC mode, and 2 of these tests actually rely on this UB. So the conclusions from those tests are not useful, and they should be redone or tested separately. So here I only used TrustInSoft Analyzer in level 1. I only used part of the features that the analyzer offers. So I didn't use exhaustive static analysis. This is for level 2. We didn't do formal verification. That would be level 3. We didn't do any integration with CI/CD, although that would be quite easy with the TrustInSoft Project Manager. And I didn't show code coverage. I didn't show a fault injection. I didn't show the data flow analysis and control flow analysis. So all of those are additional features that I didn't need to use to do all of the things that I presented today. I still got results without using those advanced features, but we likely will present those features in future episodes of Unboxed with TrustInSoft. And I think I'm done here. Gavin, back to you.
Thanks, Clement. That's very insightful. So just as we wrap up here, please add any questions that you might have in the Q&A section. We'll monitor that. And then just as a follow-up as well, if you would like to participate in one of our Code Unboxed events, by all means, please contact us at TrustInSoft. Or if you'd like a demonstration of TrustInSoft Analyzer, same thing, contact us there as well. One of the, just as I open it up for questions, one question that I know we get asked quite often, which Clement, maybe you could just run through, is explaining, you kind of touched on it, but explain a little bit more detail, the differences between L1, L2, and L3 analysis.
Yes, so L1 would be our precise analysis mode. So we essentially just run the code in a sandbox. The advantage is that it's really easy to set up. There's no dealing with precision and not a lot of parameters to level 1. Another advantage is that everything that you see, because you're just running the code, you have no false positives. So everything that you see that is detected in level 1 is a true issue of the code. But a disadvantage is that it's maybe a little bit slower, and it's only seeing the bugs that are already visible in your existing tests. And so that's why we also have level 2, which provides a wider perimeter for analysis, but also leaves the door open for false positives. And we also have level 3, which is a full formal analysis, formal proof of your code. That requires a lot more work with contract programming, but this is the most value you can get out of an analyzer like TrustInSoft.
Excellent, thanks. Last thing that I know we get asked, some of the analysis here you sped up. Typically, how long does it take for the analysis? And I know that's a loaded question.
Yeah, so here these ones are quite short. The longest one in the campaign that I showed here was 3 minutes long. I also have the ability, because I have a beefy computer and I don't have to care about licensing, but I can run multiple analyses at the same time. So that quite speeds up things a bit. So here, I think all in all, it would take about 5 minutes if I had not sped up the running of all of the analyses. I think 2 times 5 minutes during the show would maybe be a bit boring. And also I had to shorten some of the analysis. So it is possible to have analyses that take a long time with TrustInSoft. A typical analysis would be around 1 minute for a professional big piece of code.
Okay, excellent, thanks. I don't see any questions So I think what we'll do is we'll end here. And as I had mentioned, this will be available for on-demand viewing, and watch this space for the next Code Unboxed event. Thank you, everybody, for joining.
Bye.